All right, so this is Periodic Trends Part 2. Technically, we could add more if we wanted to. There's also trends for metallic character, for reactivity, and things like that. But we're just going to keep it simple. We're going to go with the major ones that basically every book covers. So in this one, we will define electron affinity and atomic size and ion size, and then we'll explain the observed trends in electron affinity, atomic size, and ion size using electron configurations and the concept of effective nuclear charge. So let's start with electron affinity, which is the energy needed to add 1 mole of electrons to a gaseous element in its ground electronic state. So for example, we could go from chlorine to chlorine minus, and that would be a change of negative 349 kilojoules per mole. So note, electron affinity can be negative. This is an exothermic change. You can also have endothermic changes. So you can have both positive or negative electron affinities. We're going to talk through some of the features of this graph. Electron affinity versus atomic number. Now, atomic number is increasing from left to right. Totally normal. But when you look at the electron affinity, the axis goes from negative numbers at the top to positive numbers at the bottom. That's the opposite of what we normally see. So why is it graphed this way? It is exothermic. The more negative it gets, the more favorable it is. So it's exothermic and favorable to have a negative value, but it is endothermic and therefore less favorable to have a positive value. So the stuff that's more likely to happen is located at the top on this graph, and the stuff that's less likely to happen is at the bottom. All right. Finally, you'll note that electron affinity can be both positive or negative. That's the 0 line on this graph. It can take energy and be endothermic, or it can release energy and be exothermic. All right, so let's highlight the noble gases. These things have full electron shells. The whole shell is filled. Valence shell, happy. It costs energy to add an electron to a noble gas because you need to open up an entirely new shell. You have to add another quantum number. All of these values below the line, inverse for normal axis. So this is less favorable, but it has a positive value. And yes, that will cause you a little bit of a headache, but hopefully we'll be okay. What about going the opposite way? What if you're going from an almost full P to a full valence shell? Okay, so that's in yellow. Those are the halogens. When you make this, it's a very large jump, right? Going from oxygen to fluorine versus fluorine to neon, that's a way bigger jump than the things surrounding it. So why is the jump this large? It is the most favorable type of electron to add because a full valence shell is the most favorable of all electron configurations. So adding that last one, definitely going to happen if it can. Still need energy, but it's exothermic. Okay, what about when we open a new subshell? So we just talked about filling a full shell or overfilling, but new subshell, so less of a jump than going up a principal quantum number. So when you go from column 2 to column 13 by adding 1 electron, so that's going from an S to a P, you're opening a new subshell. And I've highlighted each of those in green. And you can see that each of those has a very unfavorable aspect to it. It's going to cost you some energy for most of them, and it's going to be very slightly exothermic for others. So those are beryllium, magnesium, calcium, etc., alkali earth metals. And you can see that it's an exception to the overall trend. It's a dip on the graph when you do these. It takes more energy to open a new subshell because the new subshell is higher energy than the previous one. That is always the case. If you are filling the S subshell, instead of going beyond that subshell, you see the opposite effect. So in pink, we are matching up the electron on the s subshell, and that is a favorable thing to do. We like that. We're happy when we have pairs, completely full pairs in our shells. All right, so let's take a look at half-filled p orbitals. So that would be where you have all spin-up electrons completely filled, p. And in that case, you have nitrogen, phosphorus, antimony, bismuth. And as you look through this, you notice that, again, we are going less favorable. It costs us energy to start to double up electrons in our orbitals. Not a huge difference, but it's there. We know that half-filled orbitals have a more favorable configuration, and in fact we see the transition is less favorable than those surrounding it. If we go in the opposite direction, from almost half full to half full, it's that light orange, we can see that we have a more favorable situation going on. It's a consistent trend. Filling up the orbital fully, putting it halfway, these are favorable things. Going beyond, when you already are paired up, going beyond, when you have a full valence shell, that costs you energy. All right, so let's try looking at the d to p. So if you have a full d orbital and you're going up to the p, that is in magenta, and you will notice that all of those numbers are positive. And in fact, Mercury is the most positive number of all. So what is going on there? In order to make that jump, you're actually going up a full principal quantum number. Right? So for zinc, you're going from 3d10 to 4p. For cadmium, you're going from 4d10 to 5p. And for mercury, you're going from 5d10 to 6p. That's a big jump. It's a big deal. Okay? So you're going to need some energy to do that, just like you did for the noble gases. All right, what about the opposite? We're going from a full D, or sorry, a not quite full D to a full D. Those are all favorable. They're reasonably favorable, in fact. So again, we're seeing that same trend. Fully paired electrons are more stable than a mixed partially paired and full paired set. All right, so this still leaves us with some oddities in the trend, and those are in blue, light blue. These are all changes found within the D block. You remember that weird stuff when we were making our electron filling diagrams? Where in the D block, sometimes the s orbitals could shift into the d orbitals as they filled because it was more favorable to have all things half filled and stuff like that. Make sure we fill the boxes more evenly. All of these ones in light blue, that is the shenanigan going on here. That's why our trend suddenly goes upside down. Okay, so hopefully you now understand the trend in electron affinity, but let's take a moment on the next slide to look at some of these configurations that we just talked about. Okay, so let's help visualize these. So when we have our full valence shell, i.e. noble gases, and we add on another electron, we are bumping up a quantum level. So in this case, we have our full 3s argon, and we bump it up by one electron, and we fill a 4s, meaning argon minus. That is an exception, and it costs a lot of energy. If we have a full subshell, so like this case, we have a full 3s, and we're bumping up by adding an electron to the p, that is going to be a costly amount of energy. And finally, we have the spin up case where everything is spin up and then we pair it and we add another one. So if you're trying to figure out where you are in your trend in electron affinity and whether or not you should have an exception, make your orbital filling diagram. It should be obvious based on where you put your next electron. All right, so let's talk about atomic size. Atomic size can be calculated based on solutions to the Schrodinger equation. We give the radius of a particular element to the 90% confidence interval. So we say if 90% of the time the electron is in this particular amount of space, that is what we're calling the radius. So this is a calculation. Atomic radii have a pretty simple trend of increasing down and to the left. The increasing down a group makes sense intuitively. As I increase the number of electrons in an atom by increasing the principal quantum number, the atomic radii get larger. That's not surprising news. That's basically what we learned in the first place. But what about increasing from left to right across the period? This seems counterintuitive because as you add more electrons, you would think that they would take up more space, and there you would be incorrect. All of the elements across the period have the same available shells and subshells, so the orbital size is already fixed, and it's primarily determined by quantum number, principal quantum number. Within each period, each element has a different number of protons, and as you increase the number of protons, you increase the attractive force on the atomic orbitals. Therefore, at the end of each period, you have the maximum amount of attractive force for the atomic orbitals, and at the beginning of each period, you have the least amount of attractive force for the atomic orbitals of that period. In other words, the effective nuclear charge is greater when you have more protons, and it's less when you have fewer protons. Thus, in the second period, neon is smaller than lithium. Neon, lithium. And you can see that trend for all of the elements. Sodium down to argon, potassium going to krypton, rubidium going to xenon, cesium going to radium. One final note, when comparing things from different periods and groups, going down a group is a larger effect on atomic radius than going across a period. And I will only give you examples where you go down and over one or two to compare. Otherwise, it is nigh impossible unless you have a graph like this one, where it tells you basically what happens for the entire periodic table. So let's try to use that trend in atom size. Rank the following from smallest to largest. Rank each of those. So take a pause, literally pause the video, and then I'm going to go on to the next slide, or not the next slide, the same slide, but with the answers. So helium is the smallest, and then we go down the group, neon, argon, xenon, radon. The second one is going across a period, and it's fluorine, oxygen, nitrogen, carbon, and then boron. And finally, this last one is where we have a mixed case. And so the one that has the highest principal quantum number is the largest. So we go gallium, indium, tin. All right, but what about if we're doing radii of ions? When you add an electron and make an anion, the orbitals increase in size because the overall attraction of the protons to electrons is lessened per electron. In other words, the effective nuclear charge has changed. And when you extract an electron, you make a cation, the orbitals decrease in size because the overall attraction of protons to each electron is increased. Again, the effective nuclear charge goes up. So what do you think would happen if you decrease the charge further to 2-? It would get even larger. And the opposite is true for a cation. It would get even smaller. So anions are larger than neutral, which are larger than cations. But what about the trend as we go across the periodic table? So cations are smaller than neutral elements. We knew that. So cations with higher charge are smaller than cations with lower charge. But they also increase in size down a group for the same reason that the atoms increase in size down a group. What about if we're talking about anions? So anions with lower charge are larger than anions with higher charge, and the size will increase as you go down a group. So always increasing as we go down a group, whether we're talking about ions or we're talking about neutral elements. Anions are larger than neutral elements, and cations are smaller than neutral elements. So let's try to apply this. So we're going to rank from smallest to largest: sulfur, chlorine, fluorine, and chlorine minus. Okay, so we've got one anion in this little pack. And we end up with fluorine, sulfur, chlorine, and then chlorine minus. To summarize, electron affinity is the energy needed to add 1 mole of electrons to a gaseous element in the ground electronic state. The general trend is increasing down left for actual values, but if you consider which is most to least exothermic, it goes up right. Exceptions for when electron configurations go from partially filled to a mix, or partial to full, or when electrons go from completely filled to opening up a new orbital. So we'll see differences in the trend as far as what goes up and what goes down. The radius of an atom is a 90% confidence interval of that atomic size. Radii increase down and to the left. Exceptions are rare in the main block, S and P, but they're frequent in D and F. A radius of an ion is the 90% confidence interval of that ion size. Anions are larger than neutral atoms, which are larger than cations. So that means anions with lower charge are smaller than anions with higher charge. Cations with higher charge are smaller than cations with lower charge. And the size of ions goes up as you go down a group, which is exactly what you would expect. So hopefully all of these trends made sense. Yes, we could do more of them, but we're not going to because there's only so many hours of the day.